This project, a cinema analytics and prediction system, integrates multiple AI models into a robust solution for the movie industry and streaming services. Developed as a part of the Masters in Applied AI program at the University of San Diego, it combines advanced natural language processing, deep learning, revenue prediction, and recommendation techniques to deliver a holistic approach to cinema analytics. This diagram that we are seeing outlines the architecture of our cinema analytics system. We start with the data ingestion block, pulling structured and unstructured movie metadata from existing datasets in the movie database website API. Next is processing and feature engineering block, where we clean, transform, and extract features. This fit into our modeling and analytics block, composed of independent models for genre classification, movie recommendation, revenue prediction, and success classification, allowing flexibility and enabling each model to evolve or be replaced without impacting the others. Finally, we envision an operational block for deployment, monitoring, and continuous retraining, laying the groundwork for a production-ready platform.
Now let's take a look at the key data sources that power our project. We started with the Hollywood movies dataset from Kaggle, which contains details for over 4,800 films, including numerical features like budget and revenue, along with textual attributes such as movie overview, tagline, and keywords. As seen in the missing and zero counts plot, the budget and revenue fields had significant missing values. To resolve this, we fetched updated values using the TMDB APIs, which helped fill in the gaps with more reliable data. Additionally, we use consumer price index data from DataHub, which is based on releases from the US Bureau of Labor Statistics to adjust financial values for inflation. Let's look at the key insights and the features we engineer for revenue prediction and success classification. On the left, we see that movie budgets are heavily right skewed. Most films had modest budgets, while a few outliers pulled the mean up to 67 million. The median is 45 million with an interquartile range of 20 to 92 million. To manage this skew, we grouped budgets into five bins from very low to very high. On the right, revenue trends across these bins show that higher budget generally lead to higher returns, but with increased variance. This binning helped capture production scale and reduce the impact of outliers. We also added a seasonality feature. Movies released in May to July showed stronger earnings, while September and October underperformed. So we grouped months into summer holiday off-season and regular to capture summarize our modeling approach for both revenue prediction and success classification. We use the same set of features for both, including budget, budget bin, season, popularity, runtime, main genre, vote count, and vote average. All of them selected based on their correlation with movie outcomes. The dataset was split 80% for training and 10% each for validation and testing. For modeling, we used XGBoost, a gradient boosting algorithm. For regression task, we trained an XGBoost regressor to predict revenue. For classification, we built two XGBoost classifiers, one for binary classification to label movies as hit or flop, and another for multi-class classification, adding a third class, superhit, for movies earning more than three times their budget. This allowed us to evaluate how the model performs across multiple levels of slide presents our model's performance on the revenue prediction task. We evaluated three different approaches, using the mean and median revenues as simple baselines and comparing them with the XGBoost regressor. In the top chart, we compared three error metrics: mean absolute error, median absolute error, and mean absolute percentage error. We can clearly see that the XGBoost model achieved the lowest value across all three metrics. In the bottom chart, we look at R-squared scores. The baseline models performed poorly, with the median model even giving a negative score. In contrast, XGBoost achieved an R-square above 0.7, showing it learned meaningful patterns. Overall, these results confirm that the XGBoost regressor provided a significant improvement over basic heuristics and can effectively model complex revenue patterns. Look at how our models perform in predicting movie success. We began with a simple baseline using a dummy classifier which randomly predicts outcome based on class distribution. As expected, it gave flat result, around 50% across accuracy, precision, and recall. It served as a reference point to evaluate whether our real model could learn meaningful patterns. Next, the binary XGBoost model, which classified movies as a hit or flop based on whether revenue was more than twice the budget, showed a strong improvement. All key metrics rose to around 75%, showing it could clearly distinguish successful films. To test finer distinction, we added a third class superhit for movies earning over 3 times their budget. The model still performed reasonably well with accuracy above 65%.
The goal of the recommendation system is to suggest similar movies based on content, especially overviews, genres, and keywords. We implemented these three approaches: TF-IDF, BERT embeddings, and LSTM with GLOW embeddings. These natural language processing based models share many foundational components with the genre classification models that we're going to be seeing later in the presentation, including textual feature engineering, numeric metadata normalization, embedding strategies, Havre model design, feature oversampling, and multiple training iterations. TF-IDF serves as our baseline. It transforms text into sparse vectors and computes similarity using cosine distance. It is simple and explainable, but struggles with semantic understanding. It misses the connection between similar movies. In this first example for Superman, the model recommended Superman Returns and Man of Steel, among other similar thematic movies, but the similarity score of 0.59 was lower than expected. To capture deeper meaning, we use BERT sentence embeddings. These dense context-aware vectors improve semantic similarity. For example, as we inference Toy Story, the train model returns Toy Story 3 and Toy Story 2 with high similarity scores, as high as 0.93, despite different wording. BERT provides the best results in capturing themes and emotional tone. The third model for movie classification, built from scratch, combines GLOW embeddings with LSTM network and integrates numeric metadata like popularity and runtime. This hybrid approach balances language patterns with structured context. Once the model trained over 50 epochs and multiple iterations, inference from Transformers returned movies like Spider-Man 2 and Dragon Ball Evolution, showing good thematic alignment. It's more complex and needs supervision, but it offers a personalized metadata aware view. The genre classification task aimed to assign multiple genres to each movie based on its description, overview, and metadata, treating it as a multi-level classification problem. We explored two different models, a BERT-based classifier with logistic regression and a hybrid LSTM model using GLOW embeddings and numerical metadata. The BERT model produced the best overall results, especially for dominant genres like drama, action, and science fiction, with F1 scores about 0.70. This is largely due to the BERT's ability to capture semantic context even when different wording is used across movies. For example, the BERT model could correctly assign science fiction to both The Matrix and Interstellar, even when they describe their themes very differently. However, performance dropped for underrepresented or linguistically subtle genres like mystery or fantasy. This led us to the LSTM and GLOW embeddings model, which incorporated both text and movies numeric metadata. It performed better in cases where metadata strongly influenced genre, especially for family or animation films. This LSTM loss curve shows a steady decline in both training and validation loss over 100 epochs, indicating effective learning and generalization. The, the close alignment between the two curves suggests minimal overfitting, validating the model's architecture and regularization strategy. Still, The LSTM model occasionally overpredicted or underpredicted certain genres, like confusing comedy with animation or missing thriller in darker films. Its predictions were strongest when there were clear stereotypes or visual cues in the text, but struggles with ambiguous genres. In summary, while BERT excels in semantic richness, our hybrid LSTM model provided a useful insight, especially with genre imbalance. Both approaches validated that data balancing and model architecture are essential for effective multi-level classification. Before we go into our conclusion, we want to list the key findings and takeaways of this project. Bird-based models excel in semantic tasks for the recommendation and genre classification due to the contextual understanding. LSTM and GLOW embeddings show promise but requires extensive tuning and balancing to compete with BERT. XGBoost was robust for structured data in the revenue and success prediction, but struggled with multi-class imbalance. Data quality and imbalance were critical challenges, especially for underrepresented genres or extreme revenue values. Hybrid approaches, for example, combining text embeddings with metadata, consistently improve performance across models.
To conclude, our system performed well across both predictive modeling and NLP tasks. The revenue prediction model captured important patterns and clearly outperformed baselines. However, performance was affected by extreme outliers, highlighting the challenges of modeling real world revenue. For classification, the binary model gave strong results. In the multi-class setup, the model handled the added complexity fairly well, although precision for the hit class tipped due to class overlap. In the NLP part, genre classification from keywords and text worked reliably, and our content-based recommender grouped similar movies effectively, but sometimes it leaned toward very similar suggestions rather than broader diversity. Together, these components form an interlinked movie analytics system. Recommendation outputs can adapt based on predicted success, and genre insights can guide better financial predictions. Going forward, our goal is to bring all these components together into production-ready system with live APIs, retraining pipelines, and interactive dashboards. Thank you.